Hello everybody. So we were discussing about a line and a plane, and inside the head, that is line and plane, we had completed 4 articles of discussion. First of all, we understood the concept of angle between a line and a plane, after which we talked about the intersection point of a line with a plane, after which we said we are not interested in just one point of intersection between a line and a plane. Rather than that, we were interested in the entire condition based upon a line lying completely in a plane. And then we landed ourselves to the 4th very article based upon line and a plane, which is coplanarity of two lines. What is the condition which governs two lines to lie in the same plane, that is become coplanar? We had already discussed about this in the vector form. So what did we discuss? Talking about the vector form conclusion, we were talking about two lines whose equations are given to you in the vector form to be lying in the same plane. Suppose I have a plane with me. If I have a plane with me, this is any plane, inside with both these lines are actually lying. These are the two lines. This is line 1 and say this is line 2. Line 1 and line 2's equation is given to you in the vector form. This line has equation r vector equals a1 vector plus lambda times b1 vector, and L2 has equation r vector equals a2 vector plus lambda times b2 vector. Now, if these are the equations of my two lines and I am saying that these two lines are coplanar, means what? First of all, diagrammatically, visually, you can see that both these lines are lying in the same plane. Now, what are the features which we know about these two lines given by their very equations in the vector form? First of all, I know that line 1 is a line passing through a point, say A, whose position vector is a1 vector, right? You know this. The line is passing through a point whose position vector is a1 vector. Similarly, line 2 is passing through a point, say B, whose position vector is a2 vector. Also, I know that there is something which is trying to give direction to my line, and that is nothing but b1 vector, and similarly for line 2 it's b2 vector. So, parallel to line 1 is b1 vector, parallel to line 2 is b2 vector. These are the features which we know about these two lines related to their equations given to us in the vector form. Now see something very obvious. I have already discussed about this conclusion. In the last lecture we were discussing that if these two lines are lying in the same plane, keep your imaginations active. If these two lines are lying in the same plane, it's very obvious that if I talk about BA vector, B1 vector and B2 vector, there is no wonder that these three vectors are also going to lie in the same very plane. If the two lines are coplanar, it is but obvious that this vector and this vector will also be coplanar. So, if line 1 and line 2 are coplanar, that is r vector equals a1 vector plus lambda times b1 vector, and r vector equals a2 vector plus lambda times b2 vector, where obviously lambda is a parameter. This and this are coplanar. This clearly implies A1 minus A2. So mind it, this is A1, this is A2 vector. Difference of two vectors is also a vector, you know this. A1 minus A2 vector. The parallel vector to line 1, that is B1 vector. The parallel vector to line 2, that is B2 vector. All these three vectors, they are also coplanar. You know when are three vectors coplanar? We have discussed this. Three vectors are coplanar if and only if their scalar triple product is 0. So, A1 minus A2, scalar triple product of A1 minus A2, B1 and B2 is 0. What is the definition of scalar triple product of three vectors? This means A1 minus A2, first vector, dot product with cross product of the left out two vectors in this order. So, A1 minus A2 dot product with B1 cross B2, this is 0. That means what? That means you know that this is a vector and this is dot product and then this is cross product. Now, because dot product is distributive over addition and subtraction, I can write this as A1 vector dot product with B1 cross B2 minus A2 vector dot product with again B1 cross B2. This is what you get. Obviously, you can send this particular scalar to the other side. It's a scalar. We are taking the dot product of two vectors, so we get a scalar. This implies A1 vector dot product with B1 vector cross B2 vector is equal to A2 vector dot product with B1 cross B2. What is this? We had just discovered the definition in here. So again, this is equal to scalar triple product of A1, B1, B2. If this scalar product is equal to this scalar triple product, conclude that the two lines having these respectively as the parallel vectors and these respectively as the position vectors of 2 points through which they are passing, these two quantities are equal, and therefore you conclude that those two lines are coplanar. So if A1 vector, B1 vector, B2 vector, scalar triple product of these three is equal to scalar triple product of A2, B1 and B2, then conclude that the two lines L1 and L2, where L1 is A1 vector plus lambda times B1 vector and line 2 is A2 vector plus lambda times B2 vector, these two lines are coplanar. It is this which happens to be the condition. This is the required condition for line 1, which is R vector equals A1 vector plus lambda times B1 vector, and line 2 whose equation is R vector equals A2 vector plus lambda times B2 vector to be coplanar. Understood? Now that we are through with this, let me talk about one more question. See, if I have two lines with me and I have attained the conclusion that both of them are coplanar, suppose I am already in the conclusion that these two lines given to me in the vector form are coplanar, then obvious question arises, if the two lines are coplanar, that means they are lying in the same plane. Which is that plane containing these two lines? Right now, if you can understand the curiosity, I am aware about the equation of both the lines, and suppose I have landed myself to the conclusion that both of them are lying in one single plane like the diagram approaches. So, if this is that single plane containing both these lines, then what is the equation of this plane, which is containing both these lines. Let's understand that equation of the plane containing the two coplanar lines. Because see, both of them are the concepts which are intermingled with each other. First question was, given two lines, conclude whether they both are coplanar or not. If they are not coplanar, suppose our condition which we have just now developed, this condition, suppose it doesn't get satisfied, we say that the two lines are not coplanar, end of the story. But if this condition gets satisfied with these two lines, then I conclude that the both lines are coplanar. That means both the lines are lying in one single plane. And therefore, automatically the next question arises that what is the equation of that single plane containing both the lines? So that needs to be answered now. Over here, we are now running behind the answer of equation of the plane containing the lines r vector equals a1 vector plus lambda times b1 vector and r vector equals a2 vector plus lambda times b2 vector. When I am individually talking about a plane, if you can recall our very first class, first or second class on planes, we had done this very major result which is responsible in giving us equation of any plane we require. One is, get the position vector of any point lying in the plane. If you have this and you have the normal vector to the plane, both these are enough to give you the equation of this plane. So with the help of position vector of a point through which the plane is passing and the normal vector to the plane, I can get the equation of my plane, which is r minus the position vector dot n equals 0, right? That is the equation of this plane. Using this particular way of obtaining the equation of a plane, our search starts for the position vector of a point through which my plane is passing and the normal vector to this plane. Now obviously if these two lines are lying in this plane and these two lines are respectively passing through a1 vector and a2 vector, which are position vectors of points A and B, clearly these two lines are lying in this plane, so point A and point B are 2 points lying in this plane. Then what happens is a1 vector and a2 vector are points in the same plane. That means the plane is passing through this and this. I don't need 2 points, I just need a point, or I should say I just need a point's position vector. Right now I have 2 points position vector with me which are lying on this plane, right? I can use either this or this, not a problem. But just having the position vector of a point is not sufficient for me, I need the normal vector as well. Now see, this is but obvious to take the normal vector, the one that I am going to tell you. This is b1 vector, this is b2 vector. If I talk about b1 vector cross b2 vector, the story ends. Why? Because b1 cross b2 is a vector which is perpendicular to the plane of b1 and b2. Fine? I am saying b1 cross b2 is a vector which is perpendicular to the plane of b1 and b2. Both b1 and b2 vectors are parallel to L1 and L2. Entire L1 and L2 is lying in this plane, so b1 and b2 are also lying in the same plane. So b1 cross b2 happens to be a vector perpendicular to this plane. and I take this vector to be the normal vector of my plane. Obviously, normal vector is a vector perpendicular to the plane. This vector is perpendicular to the plane of B1 and B2, and B1 and B2 both are lying in this plane itself, and therefore this vector is acting as the normal vector to my plane. So then these 2 points are in the same plane, and normal vector to the plane is n vector, which is nothing but B1 cross B2. You have the normal vector with you, you have a point with you, therefore you can conclude the equation of this plane. So thus, equation of this plane is r minus a1 vector, position vector of a point through which the plane is passing, dot normal vector equals 0, or now instead of a1 vector as the position vector, I can also take a2 vector as the position vector, not a problem. And so I get or r vector minus a2 vector. Normal vector remains the same. This is the equation of the plane. That is, if I write it in a much more elaborative format, this is r dot b1 cross b2 minus a1 dot b1 cross b2 equals 0. R dot b1 cross b2 minus a1 dot b1 cross b2 equals 0. Or this is r dot b1 cross b2 minus a2 dot b1 cross b2. That is further nothing but r dot b1 cross b2 equals a1 dot b1 cross b2 obviously, or r dot b1 cross b2 equals a2 dot b1 cross b2, which means what? So because we had presented the previous condition in the scalar triple product form, I can do this in a similar fashion. This will be scalar triple product of r vector, b1 vector, b2 vector, where r vector is the position vector of any point lying in this plane, equals to scalar triple product of a1 vector, b1 vector and b2 vector. All these three are known to you, these two are known to you, this obviously remains arbitrary, representing the position vector of any point lying in this plane containing the two lines L1 and L2 whose equations are known to you. Either this is going to give you the equation, or r vector, b1 vector, b2 vectors scalar triple product equal to scalar triple product of a2 vector, b1 vector, b2 vector. This is going to give you the equation. So this happens to be the equation of this plane. Fine, and that completes our article about the coplanarity of two lines in the vector form. So we have understood what is the condition which, if gets satisfied, we can say that these two lines whose equations are given to us like this are coplanar. And once the conclusion is established about the coplanarity of these two lines, the next question can be answered very simply, that which is that plane which is making these two lines coplanar. That means which is that plane which is containing both these lines and hence making these lines lie in them. And that plane's equation is given by, the first question says that P is the image of this particular point with respect to this particular plane. So the point given to you is 3, 1 and 7, and there is this plane, and the plane's equation is x minus y plus z equals 3. Clear? Now, this is the perpendicular drawn from the point to the plane, and I am wanting to talk about its image. Say it's point P, x comma y comma z. Fine. I am saying let P be the image of this particular point with this plane, then the equation of the plane passing through P and containing this particular straight line is what? Now if this is the plane, what is the equation of normal to this plane? It is what? 1 cap minus j cap plus k cap, right? I am talking about straight line which is passing through this point and is normal to this particular plane. It is going to be very easy. It is x minus 3 by 1, equals y minus 1 by minus 1 equals z minus 7 by 1, right? So the line is passing through this point and is perpendicular to this particular plane. So it will be x minus 3 by 1 equals y minus 1 by minus 1 equals z minus 7 by 1. This is the equation of the straight line. Now I am saying that if it is a straight line which is normal to this plane passing through this point, it is actually this straight line only, and this straight line is containing this point. So this point is lying on this straight line. So the coordinates of this point can be obtained with respect to some particular variable r. What will be the coordinates? X will be r plus 3, y will be minus r plus 1 and z will be r plus 7. This is my point P. Talking about the midpoint of this particular segment, say AB or AP, say M is the midpoint. What will be the coordinates of the midpoint? It will be r plus 3 by 2. So r plus 6 by 2, which is r by 2 plus 3, comma minus r plus 1 by 2. So minus r plus 2 by 2 minus r by 2 plus 1. And then you have r plus 7 by 2, which is r by 2 plus 7. Now this is the midpoint which is obviously lying on the plane, so its coordinates will be satisfying the equation of this plane. So I am going to have x minus y plus z equals 3. So it is r by 2 plus 3 minus r by 2 plus 1. So plus r by 2 minus 1 plus r by 2 plus 7 equals 3. From here you will get r equals minus 4. The moment you get r equals minus 4, you have successfully got the coordinates of P. What will be the coordinates of P? R is minus 4 plus 3, so minus 1. Minus 4, so minus of minus 4 is 4, 4 plus 1 is 5, and minus 4 plus 7 gives you 3. Now the equation of the plane passing through this point P that we have obtained and containing this straight line is something very, very easy. What is the equation? Equation of that plane will be x, y, z, then the coordinates of P minus 1, 5, 3, and direction ratios of this line are proportional to 1, 2 and 1. So 1, 2, 1. This is what is going to give you actually the equation of the required plane, which comes out to be x minus 4, y plus 7, z equals 0. That's how you deal with this question. Let's move on to the next one. We have two lines L1 and L2 given to us. They are coplanar, then find out the value of alpha. Let's see. Let's see how do we get the value of alpha from this fact that we know that these two lines are coplanar. Now you have the two lines given as x minus 5 upon 0 equals y upon or y minus 0 upon 3 minus alpha equals z minus 0 upon minus 2 minus 0, or let me just keep it as minus 2. Then you have x minus alpha upon 0 equals y minus 0 upon minus 1 equals z minus 0 upon 2 minus alpha. Now, if these two lines are coplanar, this simply means alpha minus 5, 0 minus 0 and 0 minus 0. Then you have 0, 3 minus alpha minus 2 and 0 minus 1, 2 minus alpha. This determinant is 0. We know this. So, basically if you expand along the first row, what do you get? You get alpha minus 5. Here you have 3 minus alpha into 2 minus alpha minus 2. And now once you have this, let's just simplify this expression. You have alpha minus 5, inside you have 6 minus 3 alpha minus 2 alpha plus alpha square minus 2 equals 0. Right, this is 6 minus 3 alpha minus 2 alpha plus alpha square. So, this gives you 6 minus 2 is 4. So, you get alpha square minus 5 alpha plus 4 into alpha minus 5. This is 0. You can just split the middle term. What do you get? This is alpha square minus 4 alpha minus alpha plus 4 equals 0. So, you get alpha, alpha minus 4 minus 1, alpha minus 4. So, alpha minus 4, alpha minus 1, alpha minus 5. So, alpha can take values 1, 4 and 5. Out of that, I just have in options 1 and 4. So, these are the two correct options that alpha can take out of the available ones. Next, we have that the direction cosines of a line equally inclined with the coordinate axis are what? So, which among them is the right option for this question? Let's see. The moment I am saying that equally inclined with the coordinate axis, that means alpha is the angle which it makes with the x-axis, that is equal to beta, which the angle is made with the y-axis, which is equal to gamma, the angle made with the z-axis. That means cos alpha, which is L, equals to cos beta, which is M, equals to cos gamma, which is N. So, if L equals M equals N, which is meaning that direction cosines are basically the same, I know L square plus M square plus N square is 1, which means cos square alpha plus cos square beta plus cos square gamma is 1, but all of them are same. So, you get 3 times cos square alpha is 1. So, cos alpha basically is plus minus 1 by root 3. Right, and therefore your direction cosines become 1 by root 3, 1 by root 3, 1 by root 3. Also by concept we know each one of them is actually satisfying L square plus M square plus N square is 1. So, in here all these are the correct options. Fine. Next, you have considered the lines this and the planes P1 and P2. Let Ax plus By plus Cz equals D be the equation of the plane passing through the point of intersection of line 1 and line 2. So, let us find out the intersection point of line 1 and line 2. Any arbitrary point on line 1 will look like, so suppose I take this is equal to lambda 1. It will look like 2 lambda 1 plus 1, comma minus 1 lambda 1 minus 0, or minus 1 lambda 1, that is it. It is minus lambda 1 and then 1 lambda 1 minus 3. And any arbitrary point on line 2 will look like what? Say this is equal to lambda 2. It will be lambda 2 plus 4, lambda 2 plus 4, lambda 2 minus 3 and 2 lambda 2 minus 3. Fine. Now, this is how they look like an arbitrary point on line 1 and line 2. For which values of lambda 1 and lambda 2 will they be equal? That is going to give you the point of intersection of the two lines line 1 and line 2. So, you basically get 2 lambda 1 plus 1 equals lambda 2 plus 4, right? And you get minus lambda 1 equals lambda 2 minus 3, and you get lambda 1 minus 3 equals 2 lambda 2 minus 3. Fine. Now, over here, once you've got this, What do you think is the next step? You are going to find out the equations that are formed in lambda 1 and lambda 2 and get the value of lambda 1 and lambda 2. Lambda 1 comes out to be 2 and lambda 2 comes out to be 1, which eventually gives you the point of intersection of line 1 and line 2 as what? So lambda 1 is 2, 4 plus 1 gives you 5, minus lambda 1, so minus 2, and lambda 1 minus 3, 2 minus 3 is minus 1. Clear? I have, if this is the equation of the plane passing through this point and is perpendicular to the two planes P1 and P2. Now see, my plane is passing through this point, so its equation is A x minus 5 plus B y minus minus 2, which is y plus 2, plus C z minus minus 1, which is z plus 1 equals 0. This is the equation of the plane. Fine. Now this plane is basically, it's given that it is perpendicular to plane 1 and plane 2. Right? Plane 1 is what? 7x plus y plus 2z equals 3. So the very dot product of their normal vectors will be 0. So you get 7a plus b plus 2c. 7a plus b plus 2c is 0. And 7a plus b plus 2c is 0 and 3a plus 5b minus 6c. 3a plus 5b minus 6c is also 0. Clear? Now over here, if you apply your very cross multiplication method to get the value of a, b and c, you get minus 6 minus 10 equals minus b, then you get minus 42 minus 6. And then you have c upon, what do you get? 35 minus 3. So you basically get a upon minus 16 equals minus b upon minus 48, which eventually gives you b upon 48 equals c upon 32. So from here you get a upon 1 equals b upon minus 3 equals c upon minus 2. Fine. So you are getting a is 1, b is minus 3, c is minus 2. A is 1, so a is shaded to R. B is proportional to, or I can say A, B, C are proportional to 1, minus 3 and minus 2. So B will be matched to Q and C will be matched to minus 2, that is S. Okay. In fact, the moment you have got your A, B and C's, you can very easily get the value of D as well. What will that be? You know that this is the point lying on this plane, so you have 5 times A minus 2 times B minus C is actually equal to 0, or D. 5 times A minus 2B minus C is actually D, right? So you basically have what? 5 into 1 and B is minus 3. So plus 6 plus 2, that is 13. Are you understanding? So over here you have that this plane that you have is basically passing through this point. It is passing through this point and is perpendicular to this plane and this plane, right? And therefore you have got this equation which will be satisfied, and therefore 5 plus 6 plus 2, that is 11 plus 2, which is 13, will be the value of D. So D is coming out to be 13. So P is going to be shaded corresponding to it. Clear? Next, what you have is these lines are given to you. These lines are coplanar. So first of all, we have to verify statement 1 if it is correct or incorrect. These lines are coplanar, and equation of the plane containing them is this. For these lines to be coplanar, what do you need is 2 minus 1, then you have what? Minus 1 minus 0, and then you have 0 minus minus 1, right? Upon 1 minus 1, 1, and then you have 1, 2, 3. When you find out this determinant, you eventually get it to be equal to 0, which proves that these two lines are actually coplanar. So one step is done, that yes, they are coplanar for sure, and the equation of the plane containing them is this. Equation of the plane becomes what? Equation of the plane containing the two coplanar lines is what? It is x minus 1, y, z plus 1, 1 minus 1, 1, and 1, 2, 3. Right? So what do you get is x minus 1, and then you have minus 3, minus 2. This is minus 3, minus 2, then you have minus y. So from here you get 3 minus 1, that is 2, and then you have z plus 1. You have z plus 1, and then you have 2 plus 1. Clear? So from here you get, what do you get? You get basically minus 5x minus 2y plus 2z plus 5 and plus 2. Right? So you have 5x minus 2y plus 2z plus 7 equals 0. You want 5x plus 2y minus 3z minus 8 equals 0. Let's just check. We have x minus 1 upon x minus 1 y and z plus 1, 1 minus 1 1 and 1 2 3. So x minus 1, if I am expanding along the first row, then this is minus 3 minus 2, which is minus 5. So you get minus 5x plus 5. Right? Then you have minus y, and then you have 3 minus 1, which is 2. So this is minus 2y, and then you have plus z plus 1, and then you have 2 plus 1, that is 3. So this becomes 3. Fine. So you basically get 3z plus 3. And eventually you get what? Minus 5x minus 2y plus 3z plus 8. And when you take out the minus common, you basically get 5x plus 2y minus 3z minus 8 equals 0, and that is what is the equation given over here. So yes, the two lines are coplanar and the equation of the plane containing them is this. So statement 1 is definitely true. What about statement 2? The line this is parallel to the plane this. Now you can very easily see 1 upon 3 is equal to 2 upon 6 is equal to 3 upon 9. So yes, they are parallel. And it is given that it is perpendicular to this plane. So yes, 1 into 1, this is 1, 1 into 1 plus 2 into 1, that is 3, plus 3 into minus 1, which is minus 3, so that is 0. So that is why I can say yes, they both are perpendicular. So statement 2 is also true. But yes, statement 2 is not leading to statement 1, or statement 1 is not leading to statement 2. Fine. Therefore, statement 1 and statement 2 both are true. Clear? Next, let's see what we have. We have paragraph question now. So what does it say? A and B are 2 points whose coordinates are basically given to you. Next thing what we have is a point P moves in the space such that 3 times PA equals 2 times PB. Then locus of P is what? So see, A is given to you, B is given to you. So P is say x comma y comma z. So this is point A, this is point B. A is given to you as minus 2, 2, 3, and B is given to you as 13, minus 3, 13. 3 times PA equals 2 times PB. If you square both sides, you get 9 times PA square equals 4 times PB square. Right? 9 times PA square. So basically you get x minus minus 2 whole square plus y minus 2 square plus z minus 3 square. Fine. Then from here you have 4 times PB. So basically you get x minus 13 square plus y plus 3 square plus z minus 13 square. When you resolve this, you basically get x square plus y square plus z square plus 28x minus 12y plus 10z minus 247 equals 0 as the locus of point P. Next question says what? Coordinates of point P which divide the join of A and B in the ratio 2:3 internally are what? Let's see. So coordinates of a point which divide the join of A and B internally in the ratio 2:3. What are the coordinates of this point? You know, 2 into 13 plus 3 into minus 2. 2 into 13 plus 3 into minus 2 upon 5. This becomes what? 3 into 2 is 6. So 26 minus 6. So 20 upon 5, that is 4. Then you have 2 into minus 3 plus 3 into 2 upon 5. So you have 0. And then you have 2 into 13. 13 into 2 is 26. 2 into 13 plus 9 upon 5, which is 35 upon 5, that is 7. So 4, 0, 7, that is option number B is the correct one. Next we have what? We have equation of line L perpendicular to AB. So let's see what we have. Okay. Okay, so what was my A and B? This is my A and B. Here line L is passing through point A. If my line is passing through point A, I can say the equation of L will be somewhat like x plus 2 upon L equals y minus 2 upon m equals z minus 3 upon n. Clear? Now over here, if I talk about AB, what are direction ratios of AB? It is what? 13 minus minus 2. So 13 plus 2 is 15. Then you have minus 3 minus 2, which is minus 5. And then you have 13 minus 3, which is 10. Because this line is, it is given in the very question that the line is perpendicular to the line AB. So you basically get 15L minus 5M plus 10N equals 0. So for L equals 3, M equals 13, N equals 2, you are basically getting this is being satisfied, and therefore your correct option is option number C. Clear? Next question says that if the distance between this plane and the plane containing these two lines is root 6, then what is that mod D's value? So let's first find out the equation of the plane containing these two lines. It's very easy. It is x minus 1, y minus 2, z minus 3, and then you have 2, 3, 4, and then you have 3, 4, 5. So you basically get x minus 1 into, this becomes 15 minus 16, that is minus 1, minus y minus 2 into 10 minus 12, that is minus 2, plus z minus 3 into 8 minus 9, that is minus 1. Fine. So you basically get minus x plus 2y, isn't it? This is minus x plus 2y minus z, and then you have what? This becomes what? Minus x plus 1 plus 4 plus 3, right? So you get minus x plus 2y minus z plus 8 equals 0, isn't it? Minus x plus 2y minus z plus 8 equals 0. So you get x minus 2y plus z minus 8 equals 0. So it is given as one is ax minus 2y plus z equals d, other is x minus 2y plus z equals 8. I can keep this as equals 8. Because these two planes are parallel, just compare the equations. Ax minus 2y plus z, x minus 2y plus z. So what is the value of A? A is going to come out to be equal to 1. A is 1, and now you are saying that the distance between them is root 6. So the distance is actually mod of d. D is given to you here. Mod of d whole upon under root 1 square plus minus 2 square plus 1 square, which is root 6. This is given to you as root 6, which implies this is what? What is this? This is actually equal to, this is given to you as root 6. So this is actually equal to 6. Isn't it? Mod d upon root over 1 square plus minus 2 square, which is 5, plus 1 square, which is 6. So root 6 is root 6, because that is what is given to you, and therefore your answer is that this is equal to root 6 into root 6, which is 6. Next question we have is what? A plane is passing through this point. Okay, so there is a plane which is passing through 1, 2, 2 and is perpendicular to these two planes. So if the plane is passing through a point, if the plane is passing through this particular point, in that case, the equation of the plane is A, x minus 1 plus B, y minus 2 plus C, z minus 2 equals 0. Now because this is actually perpendicular to these two planes, you get 2a minus 2b plus c equals 0. And you also get a minus b plus 2c equals 0. Fine. The dot product of their normal vectors is basically 0. From here you get what? A upon, this becomes what? Minus 4 plus 1. Isn't it? Minus 4 plus 1 equals b upon, or I should say minus b upon 4 minus 1 equals c upon, this becomes what? Minus 2 plus 2. So you get a upon minus 3 equals minus b upon 3 equals c upon 0. Right? So you basically get what? Minus 3a, or I should write a is what? Minus 3 times x minus 1 plus, or I should again say minus 3 times y minus 2 equals 0. That is it. So you get minus 3x plus 3 minus 3y plus 6 equals 0. So you get minus 3x minus 3y plus 9 equals 0, or minus x minus y plus 3 equals 0, or x plus y minus 3 is 0. This is the equation of my required plane. It is given that the square of distance of the plane from this particular point is 51 whole square into p. Then what is p? So what is the distance? Distance is given to you as basically what it is going to be. It's 52, 53, 57. So 52 plus 53 minus 3 whole upon root over 1 plus 1. Right? Whole upon root over 1 square plus 1 square. This is given to you as 51 square into p. Right? Let's calculate this. This becomes 3 plus 2 is 5. So this is 105 minus 3, which is 102 upon root 2. Its square is basically given to you as this quantity. So what is the square of this? What is the square of this? It is 102 into 102 upon 2. This gives you what? This is 51, and this can be written as 51 into 2. 51 into 2 is 102. So this basically is 51 square into p. So p is going to come out to be 2. So your value of p is 2. It is for p equals 2 that the square of distance of this plane from 52, 53, 57 is 51 whole square into p. So practice these questions very nicely. That's it from my side. Thank you.